Hi, everybody. Welcome to our final lecture in our series for the spring. It's gone by really fast. I unfortunately missed a few of them, but I heard they've been great, so I hope you have enjoyed them. It's been really exciting to see so many people come back this year. We've been selling out each of these. Tonight's lecture sold out in the first day, basically, and so it's super exciting to see so many people back. And for next year, we're going to have to think about how we maybe get a simulcast room or something again like we did pre-COVID. So it's super exciting. So we really appreciate all the support. I want to, as always, acknowledge the support of the Norris Foundation, which really helps us cover the cost of this series. So they've been very generous through the years. And in addition to our friends, of course, here at the Huntington for hosting us in this beautiful facility. I was saying to tonight's speaker earlier today, I give talks in a lot of places, and this is really always my favorite spot. This is just an amazing auditorium to give a talk. So this is unfortunately the end, as I said, of our spring series, but I do want you all to pay attention to the fall because we have some exciting things coming up. I mentioned at the first lecture of the series that this is the 100-year anniversary of Edwin Hubble's famous VAR plate, which was the plate he used to basically discover galaxies and, as we like to say, discover the universe right here in Southern California. And so that anniversary is coming up in early October. We are planning an open house, so if you haven't visited the Carnegie Observatories campus where a lot of this work happened, that will happen in October. We don't know the date yet. We're working around because there's also a solar eclipse on October 14th. So it's a lot going on. So some of us will be going to see the solar eclipse. And I'll remind you, hopefully you are all planning to go see the total solar eclipse October 8th, which swings up through Mexico, through Texas, and kind of up through the Northeast. So if you are not going, you should work on that now. It's the last one for quite a long time in the US. And if you haven't seen a total solar eclipse, it is absolutely worth it. Anyhow. Let's get on to tonight's speaker. I'm super excited about for you to hear Ethan Nadler today. I've heard this talk before, at least a version of it. It's a great talk on a super exciting topic. Ethan was an undergraduate right here in Southern California at UC Santa Barbara. He then went up to do his PhD work at Stanford University before coming down here in 2021 as a Carnegie USC Fellow. So he's our very first Carnegie USC postdoctoral fellow. So USC, you may know, has not had a huge presence in astronomy, but this is an area that they're hoping to get more involved in. And so they've partnered with Carnegie because we obviously have a lot of resources in terms of astronomy. And so Ethan is a product of this new collaboration as our first joint postdoctoral fellow. So we're super excited about that. Ethan's work is in the area of dark matter, an area which also has a very strong history at both Carnegie and Southern California. You may know that Fritz Zwicky, right here at Caltech, and working up at Mount Wilson as well, did a lot of work. He was the first to coin the term dark matter. And then, of course, Carnegie's very famous Vera Rubin was the first to show galaxies like the Milky Way are dominated by dark matter. And today, a lot of the work on dark matter is taking place looking at smaller galaxies. And this is a work that Ethan is playing a really leading role in. And so you're going to get to hear all about that tonight. So I will get off the stage and let Ethan come out. Let's welcome Ethan Nadler to the stage. Ethan.
Good evening, everyone. Thank you for coming. As John said, I'm Ethan Nadler. I'm a joint postdoctoral fellow at Carnegie and USC, and I'm very excited to tell you how we can learn about the fundamental physics of dark matter in the sky. So I wanted to start here on my title slide, which shows the Blanco telescope in the mountains of Chile. And above the dome of the telescope in the night sky, you can see our own Milky Way galaxy at the top left hand of the screen. And in particular, what you're seeing is stars and gas in the disk of our Milky Way galaxy, the center of which is about 25,000 light years away. So it turns out that the Milky Way is a relatively average galaxy in cosmic terms. There are many galaxies in the universe that are larger than the Milky Way, but there are also many galaxies in the universe that are smaller than the Milky Way. And in fact, you can see two of them in this screen. Above the dome of the telescope, those two kind of clumps of stars and gas are known as the Large and Small Magellanic Clouds. So the Large Magellanic Cloud is about 150,000 light years away from us, And in fact, it's so close to the Milky Way that it's gravitationally bound to it. It's orbiting around the Milky Way just like the moon orbits around the Earth. And so we call these galaxies satellite galaxies. Now, if we could look at the sky with dark matter vision, we would see something like this. So what you're looking at in this image is the product of the kinds of numerical simulations that I'm going to tell you about in this talk. The brighter regions in this image are regions where there's more dark matter on the sky. You'll see it's brightest right around where the visible light was, so around our own Milky Way galaxy, and in fact, even around the Large and Small Magellanic Clouds. And very excitingly, this picture would change if we changed the fundamental physics of dark matter. So if we change how dark matter behaves at a particle level, this prediction for the dark matter distribution would change, which means that we can use observations of these galaxies in the sky to tell us about dark matter physics. So this is the story that I want to tell you today. So I've mentioned dark matter. I wish I could tell you what it is, but unfortunately, we don't know. We know that dark matter accounts for most of the mass in the universe. About 85% of the matter in the universe is dark, and only about 15% of the matter in the universe is what we're familiar with, the kinds of matter that make up galaxies and planets and stars. And everyone in this room only accounts for a very small fraction of all there is in the universe. So I want to go into a little bit more detail about this dichotomy between the visible sector, the visible matter that we know about, and the dark matter. So starting with the visible matter, we actually have a very precise theory, in some accounts one of the most rigorously tested theories ever, scientific theories ever, known as the Standard Model of Particle Physics, which describes all of the visible matter in the universe. So for example, we know that there are neutrons and protons, which are made up of quarks. There are several light generations of particles in the Standard Model, for example, electrons and muons. And there are even almost massless or totally massless particles like neutrinos and photons. So the Standard Model of Particle Physics describes to incredible accuracy how all of these particles behave, what their masses are, what their spins are, what their charges are, and how they interact with each other. And unfortunately, we have no analogous understanding of what the dark matter is. We don't even know whether there is one kind of dark matter particle or many kinds of dark matter particles. And so what we do instead is we categorize different kinds of dark matter that might exist into very broad classes of families that describe how they behave on cosmic scales. And I'm going to tell you much more about many of these kinds of dark matter later in the talk, but just to briefly introduce a few of them. So there are theories known, for example, as self-interacting dark matter, where the dark matter particles, if they come close to each other, can literally hit each other and scatter off of each other like billiard balls. There are dark matter models where the dark matter is mostly composed of primordial black holes. There are dark matter models where the dark matter is so light that it behaves quantum mechanically on cosmic length scales. So as I said, we don't know what the answer is for dark matter, but I'll show you in this talk how we've made some progress in understanding which of these classes of families of dark matter might be. So John already helped me out a little bit by introducing a bit of the history of dark matter, and I wanted to take you back first to the kind of historical evidence for dark matter before bringing you this more modern picture that I'll tell you about later in the talk. And so this historical story goes back really to the 1930s with the work of Fritz Zwicky, who observed galaxies like the Coma galaxy cluster, and in particular what Zwicky was able to observe is the speed of the galaxies as they orbit around in this cluster. And so if you know the speed of all these galaxies as they orbit around, you can roughly work out how much total mass there is in this galaxy just through the gravitational law that Newton taught us. And surprisingly, what Zwicky found was that if you compare that total amount of mass based on the orbital speeds of these galaxies to the amount of mass you would think is there just based on the total amount of visible light, the total amount of mass greatly outweighs just the visible matter by a factor of a few hundred, at least, for a galaxy cluster like Coma. So this was kind of the first hint of the need for a different kind of matter in the universe. And then later on, particularly with the work of Vera Rubin in the 1970s, this was made much more precise. So instead of galaxy clusters, Rubin observed spiral galaxies, for example, the Andromeda galaxy, which is the kind of largest galaxy close to the Milky Way. And what she observed was the rotational speeds of stars and gas as they orbit around the center of this galaxy. And once again, if you know the rotational speed, you can work out roughly how much total matter or mass there is here. And once again, this was much greater than the amount of mass you would infer just from the visible light alone. So once again, this holds for the Andromeda galaxy, and in fact, this holds for basically every galaxy we've ever observed. There is a need for matter that is not just what is there that's visible. So just to make this a little bit more visceral, I wanted to show you this movie, which shows two galaxies, sort of spiral galaxies that are chosen to look something like Andromeda or the Milky Way. And in the movie on the left, the stars and gas in this galaxy are going to orbit around with the correct amount of dark matter being placed in this numerical simulation, whereas in the movie on the right, they'll orbit around without the existence of dark matter. And what you can see is a very clear difference, right? The stars and the gas in this galaxy on the left-hand side, particularly in the outer regions, orbit around much more quickly than in the galaxy that doesn't contain any dark matter at all. So this is one way that we know that dark matter exists, and historically, a lot of the scientific literature was focused on individual galaxies or galaxy clusters like the ones I've told you about. But there's a related, although different, line of evidence for dark matter, and this is what I want to focus on in the talk, and this concerns the formation of structure in the universe. So for example, all of the galaxies, including our own galaxy that we observe. And it turns out that dark matter is what allows structure to form in the universe. Without dark matter, galaxies would have never formed, our own Milky Way galaxy would have never formed, and we wouldn't be here to ask the question of what dark matter is without the existence of dark matter itself. So it gets a bit philosophical. So to tell this story of structure formation, it's actually first helpful to go very far back in the history of the universe. Almost to its beginning, about 13.8 billion years ago, when this light that you're looking at on the screen, known as the cosmic microwave background, was emitted. So in particular, what you're looking at is essentially sort of a baby picture of the universe. This is light that reaches us from all points on the sky. It reaches our telescopes from all directions, forming a sphere. And then we project it onto a two-dimensional surface, just like you can take a globe and project it onto a two-dimensional sheet of paper to make a map of the Earth. And in particular, what we find is that the temperature of these photons, this radiation that reaches us from the cosmic microwave background, is extremely cold. So the average temperature of the cosmic microwave background is only 2.7 degrees Kelvin, so 2.7 degrees above absolute zero. But crucially, there are small differences in the temperature of the cosmic microwave background from place to place on the sky. And that's what you're looking at in this image. So the red spots and blue spots are respectively slightly warmer or slightly cooler than average. Now, the size of these variations in temperature is very small, about 1 part in 100,000 on average. In other words, the early universe was an extremely smooth place. There was very little structure in it. And this is in very stark contrast to what we observe today when we look out at the sky and we see galaxies. Both our own galaxy, the Milky Way, which is shown at the center of this image, and galaxies surrounding us in all different directions, forming this beautiful kind of cosmic web of structure. So in fact, each point in this image is a distinct galaxy at a different distance from us, essentially. And the crucial message here is that there is a lot of structure in the universe today. And dark matter is what allows that early smooth picture of the universe I showed you in the previous slide to evolve into this state with a lot of structure today. So I want to show you how we come to that conclusion. But it's helpful to kind of dig into the actual simulations we use to model the formation of structure in our universe first. And so I wanted to show you this because I actually think it's very satisfying. The physics governing dark matter is pretty simple. It's just gravity, as far as we know. And actually, we know how to solve gravity. In fact, Newton, as I said, taught us this law a long time ago, which is the gravitational force between two particles is essentially the product of their masses divided by the distance squared. So if there were only two dark matter particles in the universe, in fact, we wouldn't need a computer. We could just write down the solution to this system mathematically, analytically. And what we would find is that those particles orbit around their mutual center of mass in a way that's consistent, for example, with Kepler's laws of planetary motion. Now, if you add one more dark matter particle to the universe for a total of 3, then the situation quickly becomes more complicated. In fact, even with 3 gravitating bodies, there's no general mathematical solution for their evolution. Instead, we have to put this system on a computer and solve numerically for the evolution of these particles' orbits. But we can do that. And in fact, what we do is in modern dark matter simulations, we crank up this number of particles essentially as high as we can possibly make it using supercomputers to evolve large collections of particles that represent the dark matter distribution in our universe. So in this movie on the right, just for illustration, I'm showing you a simulation with about 1,000 particles. We refer to these as n-body simulations. But in the following slides, I'll show you modern cosmological simulations that use really gigantic numbers of particles, even 1 billion or 1 trillion. Okay, so this is really the basics with the knowledge from the last slide, plus the fact that our universe is expanding, we can run simulations that look like these. So what you'll see as these evolve, again, is a comparison between a universe with roughly the correct amount of dark matter on the left-hand side, and a universe with essentially no dark matter on the right-hand side. And what we do to run these simulations is we start them in a state that is consistent with what we observe in the cosmic microwave background. We start them how we know the universe looked 13.8 billion years ago, and then we ask, how would the universe look today? So this movie on the right, this time the regions with more dark matter are darker, and at the centers of the dark matter distribution in gold are essentially galaxies. So what you can see is that with the correct amount of dark matter, we can actually form structure, this kind of cosmic web of galaxies that we actually see when we look out at the sky, whereas in a universe with no dark matter, galaxies essentially never form. You might get lucky sometimes, but you form nothing like the cosmic web we actually see in the sky. And so this line of evidence, structure formation, is actually one of the most precise ways we have to measure the amount of dark matter in the universe. And as I said earlier, it turns out that about 85% of the total amount of matter in the universe is dark. So now, thinking about these modern simulations of dark matter, there are generally two kinds of simulations that people run. Some of them focus on relatively large regions of the universe, so most of the observable sky. As I said, with numbers of particles that are in excess of 1 billion very commonly these days. And other simulations focus on smaller length scales. So you're seeing this region of the large simulation kind of blown up successively in this slide. And it turns out that a very generic prediction of these kinds of simulations is the formation of objects known as dark matter halos. So you see an example of a dark matter halo in this slide. I'm going to zoom in on it so that we can talk about it in more detail. So this whole clump of dark matter, again, the brighter regions have more dark matter, the darker regions have less dark matter, is called a dark matter halo. And essentially what a dark matter halo is a self-gravitating system of dark matter. Its own gravity is so strong that it's held together against the expansion of the universe, even as distant galaxies expand away from it. And crucially, our modern theory of galaxy formation rests on the fact that every galaxy in the universe, we believe, formed at the center of a dark matter halo. And this is the way in which we can naturally predict these large mass-to-light ratios that Zwicky and Rubin, for example, observed. So it turns out that another prediction of our theories of galaxy formation is that larger dark matter halos, like the one you're looking at here, host larger galaxies, for example, like the Milky Way, and smaller dark matter halos, for example, like the one down here, host smaller galaxies. And I'm going to talk about these small galaxies quite a bit in the following parts of the talk because they actually turn out to be really informative for our theories of dark matter. So just to give you sort of a preview of why these tiny galaxies are so helpful, here I've shown you the same dark matter halo as the previous slide on the left, and the same halo, so starting from the same initial state, but evolved with a different kind of dark matter physics on the right-hand side. So it turns out that our standard theory of dark matter, we usually refer to as cold dark matter, which is really just a placeholder for a kind of dark matter that is very boring. All it does is gravitate, and there's no other physics associated with it. And if you only have gravity, you can form structure down to very small length scales, which is why you see little tiny clumps of dark matter in the image on the left, down to very small scales. Whereas, if you change the fundamental particle physics associated with dark matter, you generically change what this prediction for small-scale structure looks like. So in this simulation on the right, what we've done is we've reduced the mass of the dark matter particle enough so that it's produced in a state that we call warm. And by warm, we just mean that it moves quickly when it's produced in the early universe, which allows it to escape the smallest clumps of dark matter before they have the chance to bind together gravitationally. So this is why, in the image on the right, you see many fewer clumps of dark matter, particularly many fewer small clumps of dark matter, than in the simulation on the left. And what we can do then is associate those clumps of dark matter with the galaxies we expect them to host, look at the sky, and ask how many of these tiny galaxies do we actually find, and in this way test our assumption about the dark matter particle physics. So as I said, I'm going to come back to this in much more detail, but first I have to tell you the story of how we actually can find these tiny galaxies, because it's very challenging observationally. So particularly over the last couple of decades, our observations of small galaxies, or dwarf galaxies, has improved rapidly. And what these observations have revealed is really a wealth of structure on small cosmic scales. So going back to this picture of the Milky Way galaxy, it turns out that the Milky Way contains roughly 60 billion solar masses. This is a typo, 6 billion solar masses. No, 60 billion. Okay, we're good. 60 billion solar masses worth of stars and gas. And there are two smaller galaxies, again, shown in this image, the Large and Small Magellanic Clouds, which, as I said, are much tinier than the Milky Way. So respectively, this confirms that it was not a typo. Respectively, they weigh 3 billion and 1 billion solar masses, roughly 1/10 the mass of the Milky Way. So in fact, we've known about the Large and Small Magellanic Clouds basically forever. As long as humans in the southern hemisphere have looked up at the night sky, they've noticed these galaxies. The first documented recording of the Magellanic Clouds came in the Book of Fixed Stars. This was written by a Persian astronomer in 964 AD. And then their namesake, Ferdinand Magellan, documented them pretty extensively as he voyaged around the southern hemisphere in the 1500s. So if we make a graph of the number of these small galaxies that we've observed around the Milky Way on the vertical axis versus the year we've discovered them on the horizontal axis, we find something like this. It starts out at 2 because we've known about the Large and Small Magellanic Clouds forever. And then in the 1900s, we discovered a new population of these satellite galaxies orbiting around the Milky Way. This is an example of one of these galaxies. This is known as the Sculptor dwarf galaxy. And this is even smaller. So Sculptor contains about 4 million suns worth of mass, which makes it a factor of even 1,000 smaller than the Magellanic Clouds. And the astronomer who discovered this galaxy, Harlow Shapley, in 1938, wrote that Sculptor appeared to be unlike any known stellar organization, and that a general description of these kinds of objects, namely dwarf galaxies, was of interest. And this is incredibly prescient for someone writing in 1938, because these are the galaxies we use today to test our theories of dark matter. So something pretty remarkable happened in the early 2000s after the discovery of these classical galaxies in the 1900s. And this was essentially enabled by digital imaging. So surveys like the Sloan Digital Sky Survey, which took data in New Mexico, were able to automate the search for these tiny galaxies, for example, over the entire or much of the northern hemisphere. And they were also able to find galaxies that were much smaller and fainter than we had been able to detect before. So this image actually contains an example of one of the dwarf galaxies that the Sloan Digital Sky Survey discovered. But you should not be able to see it by eye. Hopefully you can't anyway. I'm going to help you out by circling the stars in this image that are actually members of this galaxy, which is known as Segue 1. So Segue 1 is a galaxy that has about 300 suns worth of mass. Essentially, it's one of the darkest galaxies that we've ever discovered. It's many million times less massive than, for example, the Milky Way or the Large Magellanic Cloud. And I want to tell you how we can actually, what right do we have to call a system like Segue 1 a galaxy when it contains only a few hundred stars? And so the answer can be understood, again, by thinking about the total amount of mass in stellar systems versus the amount of light that they have. So again, if we think about galaxies like the Milky Way from the work of Rubin, for example, we know that they have about, very roughly, 10 to 100 times the amount of dark matter that they have normal visible matter. And as we go down to smaller and smaller galaxies, so down through the Magellanic Clouds, down to these classical satellite galaxies that were discovered in the 1900s, finally we arrive at these ultra-faint dwarf galaxies like Segue 1, which have mass-to-light ratios that can be as large as 1,000 or even more. So 1,000 times more total matter than they have visible matter. And this is the crucial distinction between systems like Segue 1 and other small clumps of stars that might have similar total stellar masses, but are not consistent with being dominated by dark matter. So for example, globular clusters and other kinds of star clusters have similar stellar masses as the ultra-faint dwarf galaxies, but essentially they don't have any dark matter. And so this is why we call a system like Segue 1 a galaxy. Essentially, we define a galaxy as a collection of stars whose motion is consistent with being dominated by dark matter. Now, after the Sloan Digital Sky Survey stopped taking data, and after those discoveries were made, a new generation of surveys came online, this time more recently. So this, again, is the telescope that I showed you in the first slide. This is the Blanco telescope. And it conducted this survey known as the Dark Energy Survey, which was really revolutionary for the discovery of these tiny galaxies, this time in the southern hemisphere, near the Large and Small Magellanic Clouds. So the reason that the Dark Energy Survey was so powerful essentially came down to its camera. Just for context, a typical camera, for example, in your iPhone, might be able to take images that contain 12 million pixels. The camera that was used to conduct the Sloan Digital Sky Survey can take images with about 10 times more pixels, so 120 million pixels per image. And the Dark Energy Survey used a much more powerful camera that could take several times more pixels per image and collect these pixels over a relatively wide field of view. So this combination of depth and area was really fantastic for searching for these tiny dwarf galaxies, and the Dark Energy Survey and another collection of surveys really delivered on this promise of discovering tiny dwarf galaxies. In particular, it brought the total number of these small systems that we know of up from roughly 27 after Sloan stopped, up to now well in excess of 60. This slide is actually a couple years old, and there are new discoveries all the time. One thing that you'll notice here is that not all of these new discoveries are filled in as confirmed dark matter-dominated dwarf galaxies, because we don't yet have the follow-up data needed to say that they're dominated by dark matter. They might be star clusters. But in fact, as I said, this slide is a couple years old, and these are being filled in all the time. So the upshot is that we now know of over 50 of these dark matter-dominated tiny galaxies orbiting the Milky Way. And if we plot them on the sky, it looks something like this. So they're all over the place, particularly in the southern hemisphere, because that's where we've been able to observe the sky to great depth, right around the Large and Small Magellanic Clouds. Okay, so now with this setup, I can tell you about how these tiny galaxies allow us to learn about new dark matter physics. First, I have to come back to the simulations for a moment, because I've been focusing on the Milky Way. Essentially, we can only detect these really tiny galaxies, like the ultra-faint dwarf galaxies, close to us because they're so faint. So we need simulations that actually model the formation of systems like the Milky Way rather than some random region of the universe. So what you're going to see in this movie is the formation of the dark matter structure underlying the Milky Way. This is a simulation that I ran a few years ago. And in particular, if you focus at the center of the movie, you'll see the dark matter halo that hosts our Milky Way galaxy forming. And you'll also see an analog, simulated kind of version of the Large Magellanic Cloud forming its own dark matter and then falling into the Milky Way towards the end of the movie. So first, if you focus at the center, the first thing you'll see is the Milky Way undergoing a major collision, a large merger with another galaxy about 10 billion years ago. And this collision is actually now supported by data that we have. Something like this actually happened to our own galaxy 10 billion years ago. At the end of the movie, you see the Large Magellanic Cloud falling into the Milky Way. And in fact, in this simulation, it falls into the Milky Way on an orbit that is consistent with what we actually observe the Large Magellanic Cloud is doing in the sky. So this kind of simulation gives us a prediction for the dark matter structure underlying the Milky Way. And it gives us a way to connect the visible light we see in the sky with the dark matter structure we believe is underneath. So now I'd like to come back to this dichotomy between cold dark matter and different kinds of dark matter models, for example, like warm dark matter, and just remind you that the crucial difference between models where dark matter only gravitates and models where we introduce new physics, for example, a high initial speed of the dark matter particles, is that these alternative models, rather generically, form less structure on small scales. They form fewer of these small dwarf galaxies. So in fact, we can do something that is conceptually very simple. We can look at the sky, count the number of these tiny dwarf galaxies that we observe, and then ask, how warm can the dark matter be to actually have produced the number of galaxies we observe, in this case, 60 dwarf galaxies around the Milky Way? So I'm going to walk you through a series of results from analyses that I led. First, I want to tell you that we can actually combine this data from dwarf galaxies with data from other probes of small-scale dark matter structure. One of these kind of complementary techniques is known as strong gravitational lensing, which is really just the idea that mass bends the paths of light. So if light that we observe, for example, from a very distant bright source, like the region near a black hole, travels to us, its path will be bent, and the amount of bending depends on the amount of dark matter between us and that distant galaxy or light source. And so, based on the amount of bending that we actually observe, we can again kind of discriminate between these models where dark matter has a lot of structure on small scales, like cold dark matter, and models like warm dark matter, where there's much less clumping of dark matter on small scales. So this series of analyses was actually combined with the dwarf galaxy data. This is work that I've done, for example, with Andrew Benson at Carnegie. And what we found is that if you think about warm dark matter, for example, so you ask the question, what was the temperature of dark matter in the early universe? It turns out that dark matter cannot be too warm when it was produced. And the reason is that if dark matter were too warm, we would not observe the number of dwarf galaxies that we actually see when we look at the sky. And the amount of bending in the strong gravitational lensing data would not be compatible with what we actually observe when we look at the sky. So just quantitatively, the way we usually quote this kind of result is a limit on the mass of the dark matter particle. It turns out that you can place a lower limit on the dark matter particle's mass of roughly 10 kiloelectron volts. And another way of saying that is that the dark matter could not have been warm as soon as a few months after the Big Bang. So we're reaching very far back in time by doing these analyses and probing how dark matter was behaving just a few months after the Big Bang using galaxies today. The very exciting thing about these kinds of analyses is that they inform theoretical models of dark matter. So for example, particle physicists for many decades have been writing down models where dark matter is an additional kind of neutrino. I mentioned the neutrinos earlier, which are the very lightest particles we have in the standard model. And if the dark matter is kind of a cousin of the neutrinos, but a little bit more heavy, then it can be kind of consistent with being the dark matter we observe. But it turns out that neutrinos, these kind of sterile dark matter neutrinos, are often produced in a very warm state. So large classes of these models have been ruled out by these kinds of dark matter constraints. So now I want to come to a slightly different question. This is probably the most quantitative plot that I'll show you, but I hope you can kind of bear with me here. I'll walk you through it. So the question now is, how strongly could dark matter interact non-gravitationally with standard model particles? So in the cold dark matter model, for example, if a dark matter and a proton come near each other, they only gravitate. The only force they feel is the mutual gravitational force between those particles. But we can ask the question, what if when a dark matter particle comes near a proton, it can actually scatter off of it, again, like a billiard ball? What if those two particles can hit each other, collide, then go their separate ways, having exchanged energy and momentum? So what you see in this plot on the vertical axis is the mass of dark matter particles that we consider, and on the horizontal axis is the interaction strength between dark matter particles and protons, where higher numbers here means stronger interactions. And the shaded regions are parts of this parameter space that have been ruled out by various types of experiments. So in particular, these gray regions on the right-hand side of the plot, and particularly this bottom right-hand side, have been ruled out by experiments known as direct detection experiments. These are actually conducted on Earth. Essentially what you do is you build a gigantic vat of a noble gas, like xenon. You stick it way underground, and then you wait for a dark matter particle to come into that vat and hit a proton, producing an observable signature. And we've never seen that, which is why this entire gray region is ruled out. And in fact, this gray region extends many orders of magnitude to below and to the right of where I can plot here, ruling out classes of models, for example, known as weakly interacting massive particle dark matter. There are also a couple other shaded regions on this plot. So in the green, you see the cosmic microwave background again, which I introduced earlier. It turns out that if dark matter particles can collide with protons, they also mess up the structure we observe in the cosmic microwave background, so you can rule out these upper regions of the plot. And then in the blue and red are the regions we've been able to rule out using our analyses of the dwarf galaxies around the Milky Way, which improve over previous analyses by many orders of magnitude, ruling out dark matter-proton interactions that are thousands of times weaker than what we were able to test before. and are also entirely complementary to direct detection experiments. It's very difficult for these terrestrial experiments to probe the region of parameter space that we're actually testing with dwarf galaxies. So this is work that is being led quite a bit out of the USC group. I've done a lot of this with Vera Glusovic, who's a professor there. So I want to give you a little bit more detail about the work we're doing right now on actually refining our predictions and models for these classes of dark matter that interacts with standard model particles. And the first, again, is in terms of simulations. So it turns out that running really large numbers of simulations at different points in that parameter space that I showed you earlier is helpful because it allows us to more precisely predict what the structure of the universe would be under the assumption of a given dark matter model. So what you're looking at here, again, is sort of a baby picture of the universe, this time a numerical one. It's on our computers. And what you see is kind of density ripples in the early universe. So the slightly darker regions have slightly more dark matter, and the slightly lighter regions have slightly less dark matter. What our simulations do is evolve this early state of the universe into a system like the Milky Way, with its dark matter halo and even the dark matter halo of the Large Magellanic Cloud just above it. And it turns out that if we change the structure of the early universe very subtly, so I'll flip back and forth a few times if you focus on the plot on, if you focus on the plot on the left-hand side, changing the structure of the early universe at early times just a little bit has really drastic consequences for exactly how much structure we expect around our Milky Way today. So we've run now, actually using supercomputers that are just down the road, the largest collection of these simulations that has ever been run, and we're using these to kind of refine our tests of these interacting dark matter models. There's another question we can ask about these models with dark matter proton interactions, for example, and that is, would there be any signatures of this new dark matter physics today? Because, for example, there are a lot of protons in this room, and we expect there are also dark matter particles passing through this room. So this movie is going to show you the formation of a disk galaxy that resembles the Milky Way, under the assumption that these interactions between dark matter particles and protons actually occur. So this is going to play a few times. What you're seeing here in blue are clumps of gas in the center of our Milky Way galaxy. And each blue dot here represents very roughly 1 million solar masses worth of stars and gas. And these red particles are clumps of gas that have been hit by a dark matter particle, because in these models, we assume this can happen. And you'll see some really interesting effects. So for example, if you focus on some of the red particles, they're essentially kicked out of the galaxy, and they fly out and escape. Another way of thinking about this is that our Milky Way galaxy would be evaporating in these kinds of models. And other ones are kind of stuck in the center of the galaxy. So these simulations are exciting because we can use them in conjunction with data mapping out the history and the current state of the actual Milky Way galaxy to ask the question if there's evidence for these kinds of interactions. So for now, all we have, again, is a kind of limit on how strongly these interactions can actually occur. So if we think about the interaction strength between dark matter and normal matter, the answer for now is that the interactions can't be too strong. And as I said, this informs theories of dark matter, for example, weakly interacting massive particles. Now, I don't have time to go into too much detail about the next row here. I'm very happy to answer questions about it, though. But essentially, you can ask an analogous question for dark matter interactions with other dark matter particles. And I mentioned this at the beginning in the context of self-interacting dark matter. And again, the story here is actually a little more subtle, but again, it by and large turns out that the dark matter can't interact too strongly with itself. So for all we know, dark matter only gravitates both with itself and with particles in the standard model. So the last kind of dark matter physics that I want to tell you about is really very cool, and it's received a lot of attention over the last few years, and this concerns the mass of dark matter particles. So in the standard picture of cold dark matter, essentially what we assume is that dark matter particles are heavy enough that they are well described as being particles. But quantum mechanics teaches us that there's actually a duality between particles and waves. Every particle looks like a wave if you zoom in closely enough, or correspondingly if you reduce the mass of the particle enough. So there's this notion of the de Broglie wavelength, which is essentially what is the length scale at which quantum mechanical effects become relevant. And it turns out this is inversely proportional to the mass. So if you make the mass of a particle really small, it's going to behave like a wave at larger length scales. And that's what you can do in classes of dark matter. Because we don't know what the mass of dark matter particles is, you can ask the question, what if they're really light? And what if they actually behave like waves on the scales we observe on the sky? So here you're looking at a simulation where on the right-hand side, the dark matter is behaving like waves that are interfering with each other. And on the left-hand side, it's just behaving like cold dark matter. And a very generic prediction, if something behaves like a wave, is that it will destructively interfere with itself. And so once again, you predict less structure on small scales. You'll see on the right-hand side, there are less of these kind of yellow, high-density regions of dark matter. And once again, you would naturally predict in these sorts of models to reduce the number of dwarf galaxies that we actually see around the Milky Way. So then, once again, we can place a limit on the mass of the dark matter particle. And this time what we can say is that the dark matter particles can't be too light. And technically what this means is that the dark matter particles can't be lighter than 10 to the minus 22 electron volts. So that's roughly 20 orders of magnitude lighter than any particle we know in the standard model. So this is not a very constraining limit, but it's still a limit. But nonetheless, it informs theories of dark matter, for example, where the dark matter is a kind of axion. And these models where dark matter is an ultralight axion are naturally predicted, for example, by string theory. Okay, so now I want to end on a slightly more optimistic note. I told you about a lot of different constraints we have on the behavior of dark matter. But I want to end by telling you how new generations of telescopes will really transform the search for dwarf galaxies and also more generally our quest to kind of map out the small-scale structure of the universe, potentially enabling discovery of new dark matter physics. So it's helpful to think about the dwarf galaxies that we have observed in this parameter space of their brightness or luminosity on the vertical axis and their distance from us on the horizontal axis. So galaxies like the Milky Way or Andromeda are observable at very large distances. In fact, as I'll tell you in the next slide, we can even observe those kinds of galaxies in the very early universe. But as you go to fainter and fainter galaxies, like the Magellanic Clouds, again, down through the classical satellites and down to the ultrafaints, we can only observe these tiny galaxies currently that are very close to us, just because of the observational sensitivity of our telescopes. So essentially, our current observations form a kind of boundary in this parameter space below which we haven't been able to probe yet, but which new generations of telescopes and facilities like the Rubin Observatory, the Roman Space Telescope, and JWST will probe. So I want to just give you a few examples and show you how these facilities will improve our ability to detect these tiny dwarf galaxies. So starting with JWST, you've probably heard quite a bit about this, particularly if you attended previous lectures in the series. And what JWST is great at is detecting galaxies at really early times, so only a few 100 million years after the Big Bang. The reason it's so good at this is that it's a near-infrared telescope in space, so it has extremely good resolution for these kinds of wavelengths. And what it has already found, very excitingly, is that there are lots of these sort of bright galaxies. You can think of these as kind of ancestors of our own Milky Way galaxy at early times, as I said, only a couple 100 million years after the Big Bang. And this is kind of challenging our theories of galaxy formation. And very crucially for this dark matter story, it forms a link, right? Because we know how the Milky Way looks today, and we want to be able to connect how it looks today to how it looked in the early universe. This is a very important part of our theoretical models for dark matter, which is why these observations are extremely helpful for this dark matter detection quest. Next, I want to talk mostly about the Vera Rubin Observatory, which is being constructed, again, in Chile. You see a picture of it here fairly recently. And this facility will be really amazing for discovering these tiny dwarf galaxies. Our current forecasts suggest that Rubin will be able to discover essentially all of the remaining ultra-faint dwarf galaxies orbiting around the Milky Way in the southern hemisphere, which is where it will look. The reason it can do this is largely because of its camera. So the camera on Rubin is able to take images with 3.2 gigapixels. So that's a crazy number. I mean, that's the largest digital camera that's ever been built by humankind by far. And in addition, Rubin will survey roughly half of the sky, so the entire southern hemisphere, about once a week. So the combination of that sort of cadence of observations with the extreme sensitivity that you get from a 3.2 gigapixel camera is going to make it incredibly powerful for finding these small galaxies. So to give you kind of a teaser for what Rubin can do, this is a region of the sky that was imaged by the Sloan Digital Sky Survey, focused on this galaxy at the middle. And now if I flip to the same region of the sky, but imaged at the sensitivity that Rubin will be able to achieve, it looks something like this. So you'll see that tons of faint stars that weren't visible previously pop out. And in addition, the structure of the galaxy, for example, at the center is resolved much better at the depth Rubin will be able to achieve. So this is only one small patch of the sky. This kind of transformation will happen, as I said, over the entire southern hemisphere roughly once a week. So it's really incredible what's in store. And Rubin is slated to start taking data hopefully within the next year and a half or so. And finally, I want to mention the Nancy Grace Roman Space Telescope, which is also slated to start taking data hopefully within the next few years. It's also a sort of infrared telescope, slightly similar to James Webb, a little bit different. But the really amazing thing about Roman is its field of view. So this kind of cutout here, circled in white, shows the region of the sky, the size of the region of the sky that Roman will be able to observe. And the little box here in the center is the field of view of the Hubble Space Telescope, which was sort of the best thing we had before Roman. So the area of the sky covered by Roman images is roughly 100 times that of Hubble, which is going to be really incredible, both for detecting tiny galaxies near us and ones that are farther away. So the combination of these facilities, in particular Rubin and Roman, we expect will, again, more than double the number of these tiny galaxies around the Milky Way, hopefully within the next decade or so. And also, excitingly, related to the strong lensing story that I told you, these facilities will discover thousands of new strongly lensed galaxies, which can be used for dark matter analyses as well. Okay, so that's all I have. To conclude, I wanted to remind you that dark matter allows all structure we observe in the universe, including galaxies and us, to form. Observations of the very smallest galaxies have revealed, particularly in the last couple of decades, a wealth of cosmic structure on small scales. New dark matter physics beyond gravity can appear in the sky, and we believe that next generation telescopes may reveal the fundamental nature of dark matter. So thank you very much. Happy to take any questions.
Excellent. So we have a couple microphones. We ask if people can go on the sides and ask their questions into the microphone so everybody can hear them.
So you were talking about, it seems like the hope in the future is with all these observatories and with our processing power getting better, that we can make better models and better simulations. Is there any hope for anything? I think you said direct observation. Are there any instruments that are promising at all that we can do direct observation here? Is that a possibility?
Yeah, definitely. So maybe I should repeat the question. I think the question is essentially, rather than cosmic observations, how can we directly detect the dark matter, and what new technologies?
Yeah,
are there?
you said we use the basically we use the thing underground basically to see if we could detect it, and it came back with nothing.
Yeah, exactly. Yeah. So I think there are a couple things to say here. First is that those direct detection experiments that I described are also rapidly improving. And in particular, they're able to extend to those lower dark matter masses that they haven't previously been able to cover. The reason for this is essentially better detector technologies. And so, for example, rather than dark matter scattering off of protons, you can start to ask the question of, can dark matter scatter off of electrons, for example, which are much lighter with these kinds of technologies. Another thing to say is that models like axions, for example, this is just one example, can couple. So in addition to interacting with protons, there can actually be sort of electromagnetic or cousins of the electromagnetic interaction in those models. So you can search for modulations, for example, to like radio waves as a signature of dark matter physics. And there's lots of work going on in this direction as well, kind of downsizing experiments in that regard. Yeah. Yeah.
Oh, hello, thank you. I was wondering if you could elaborate more where dark matter is most dense within the galaxies themselves. Does that prevent then dark energy from forcing the expansion of galaxies themselves and leaving that just to the space in between the galaxies as this expansion that we're experiencing?
Yeah, that's actually exactly right. So at the centers of galaxies where the dark matter dominates the gravitational potential, those regions stay gravitationally bound together despite the fact that dark energy wants them to expand. So in the far future, like here on Earth, we're going to stay gravitationally bound, actually. All of the distant galaxies in the universe will expand away from us, but we stay bound, and then we just can't see the distant galaxies anymore. So it really resists even the force of dark energy in that sense.
Very good, thank you.
Yeah.
Yeah. Is there a theorist hiding somewhere considering how cold dark matter either gets cold or starts cold when the Big Bang is about the hottest thing you can think of?
Great question. There are many theorists thinking about that. They're not hiding. Many cosmologists think about this. So the key is that dark matter's interactions with basically everything have to be weak. And this is actually, I didn't really tell you the whole story underlying the dark matter-proton interactions, but this is the reason, exactly what you said, this is the reason why dark matter that scatters off of protons essentially becomes warm. It becomes warm because the rest of the universe is warm at early times, so if you allow even a very small amount of interaction between the dark matter and everything else, it heats up the dark matter. So the key is that the dark matter has to be produced in a cold state, and it can't interact too much with everything else.
Yeah, we've got a question from the live stream. Someone would like to know if there are theories of dark matter interaction that would reveal interactions in the accretion disks around black holes.
That's, yeah, very interesting question. So actually, again, that goes back to those kind of axion or axion-like dark matter models that I mentioned. So because those models have, as I said, analogs of the electromagnetic interaction, then in regions with very large, for example, magnetic fields, like right around the center of the black hole, of a supermassive black hole, you can potentially see signatures of that kind of dark matter physics. Again, we haven't seen it, so we don't have evidence for that kind of thing, but there is an ongoing observational effort to do this. Yeah.
So I think I heard you just say that under certain circumstances, dark matter might modulate the electromagnetic spectra, and we could detect signatures there. That sounds too easy for us to detect with ordinary instruments. I know there have to be some catches.
Yeah, the catch is essentially that if that kind of interaction exists, it has to be many, many orders of magnitude weaker than the other kinds of interactions I was telling you about. So if it exists, it has to exist at a very, very minute sort of level so that we haven't seen it obviously yet.
Will it be easier or harder to see than, say, gravitational waves? How much sensitivity do we need to see modulation in the EM spectra?
Yeah, I think it's a hard question. I mean, observationally, if something is screwed up electromagnetically, generally that's easier to see. But again, you can just push these interactions to be extremely weak. So I guess what it depends on is what the dark matter is actually doing. That'll determine whether we see it first gravitationally or, for example, electromagnetically. Yeah.
Great. If we don't have any more questions, let's thank Ethan again. Oh, one more question. Sorry.
Yeah. I just have two trivial questions. The first one, how does the rotation of the galaxy relate to the amount of dark matter compared to two galaxies rotating each other?
Do you mean two galaxies rotating around each other?
Right.
So if two galaxies are rotating around each other, I mean, the rotation speed is determined by the total amount of mass those two galaxies have. But even in that case, each galaxy would have a dark matter halo that is much more massive than either of the galaxies alone. So really, gravity is always dominated by the amount of dark matter.
Right, but they do correlate, you mean?
Yes, it's the same law.
There's the same amount of
gravitational
dark
physics.
energy
Yeah.
would predict both.
Yeah.
The other question is, how does the amount of dark matter predict through the evolution of the universe? Sorry.
Yeah. So in terms of the evolution, I mean, so I showed you, for example, this story of like structure formation in the cosmos. That is how the dark matter has the most impact. So in the early universe, for example, at the time of the cosmic microwave background, the dark matter was not the dominant factor. The dominant factor was really the normal matter, like protons and electrons and photons. Dark matter after the time of the cosmic microwave background is what allows structure to form efficiently. So that's the biggest impact it has in the evolution of the universe.
So how does it relate to the amount of dark matter then?
The amount of dark energy or dark matter?
No, dark matter throughout the evolution of the universe.
Oh, sure. So if there's more dark matter, then structure forms more quickly and earlier on. And we form more structure. If there's less dark matter, then we form less structure.
Yeah, but I mean, so it means that the dark matter was more prevalent, or, you know, so it's like being created throughout the evolution of the universe, or it was constant, or the distribution of it?
Yeah, so
is
it had
changing or
to,
what?
yeah, so most, almost all of the dark matter that we actually observed, so this kind of 85% number, had to be there already by the time of the cosmic microwave background. In fact, it had to be there only a couple months after the Big Bang, like I was mentioning, because otherwise it would have been too warm. If you try to produce dark matter too late in the evolution of the universe, it's generically produced in a warm state, which actually goes to the other question as well.
Okay, thank you.
All right, let's thank our speaker. I should have said, if you're not on our mailing list for Carnegie and you want to know about our fall events, please, there's little cards outside. You can grab one and sign up, please, so that way you'll know about our open house and other